Okay. I've been asked to look at a homework problem here before we get started. I probably don't have time to do an entire problem here in class, but time to set things up and make sure we know what direction we're going and how to approach this. So we have a baseball slugger hits a pitch and watches the ball reach into the bleachers for a home run. That is poor sportsmanship, right? Somebody is going to get beamed with a baseball if you do that. You run and pretend like you don't know it's going to be a home run until it's a home run, and then you still keep running, just not as fast. If you go too slow, once again, somebody's going to get hit. Okay, so this is written by a physics person, probably not up to date on the rules of baseball, the unwritten rules. So it lands 7.5 meters higher than it was hit. When visiting with the fan that caught the ball, he learned the ball was moving with a final velocity of 32.25 meters per second at an angle 27 degrees below horizontal, because all fans have the ability to measure the speed to centimeters per second precision. And the angle, of course. I mean, it's a given, right? Assume the ball encountered no air resistance. Okay, we've already had enough ridiculous stuff. There's no problem with going that much further. And use Cartesian coordinate system with the origin located at the ball's initial position. Now let me start at the end. I know I kind of made fun of this, but we do physics problems to make them easy for you, as compared to making it harder. So this is the easy version of this problem. If you had to include air resistance and whatnot, it would be harder, right? What does it mean to say a Cartesian coordinate system?
XY.
Okay, Cartesian coordinate system is our standard XY system. So we're going to use a Cartesian coordinate. Our X and our Y coordinates are going to be based on the location of the ball when it left the bat. So it tells us where to make our reference point. Usually we don't tell you where to make the reference, but that would be the easiest point to choose for making the reference, because the starting point is 0, 0. So this is kind of guiding you in something that's a good practice to make your life easier by choosing 0, 0. Now, if something falls to a lower position, I usually actually say the starting point is 0 in the X and something positive in the Y and ends at 0. But that's personal preference. Okay, so then I need to calculate, first of all, an expression for the ball's initial velocity in terms of the variables given in the problem statement. So I need to think about this before I do anything further. And first, list the things you know and don't know. Now, first it would be draw the figure, but it's already there. So I'm going to write the things I know and things I don't know. So what do I know? Okay, so I have the velocity vector, so I'll put the vector sign over it. Acceleration is minus g in the y direction.
And the x direction is 0.
Yeah, I wrote as a vector, so that implies.
What does the parent mean again?
That means that it has a magnitude of 1 and is only indicating direction. You're welcome. Okay, there's only one other thing we know. We know y final, well, the theta was right there. We know y final is 7.5 meters. So there I have what I know.
My final is 32.25.
No, that was Vy, or V final.
H is 7.5.
Yeah, which is y final. Yeah.
You also know y.
Same thing. H is y final minus y initial, but they told us to use y initial is 0.
It's far too confusing. But okay.
Okay.
Yeah, I know.
Dave's all, I didn't want to do it that way. All right, so we have to think about how to do this. So how to do this, it's going to turn out to be an easy calculation. The how to do it is the question that's hard. we're asked to first create an expression for the ball's initial velocity in terms of the variables given the problem statement. Well, as the ball is flying through the air, my ball is still, that's probably not Nathan's car anymore, he's probably thrown it away by now. But let's say it's this. As this flies through the air, okay, Russell, you don't have, well, you do too. Okay, Randy's going to trust me to not hit his Surface Pro. There we go. That's appropriate. We're making confidence on it. So as I throw this to Randy, what can you tell me about its vertical and horizontal motion as it was going through the air? What would you tell me about its vertical and horizontal motion as it's going through the air? Okay, it had both.
You break out the final velocity into your x and y components, you can find it.
That is going to be our method, yes. But I want to lead people to how we come to that conclusion. So what can you tell me about, let's say, the vertical component of its velocities it was flying from me to Randy?
It went up and back down.
First, it had an upward vertical velocity, then it was 0 at the top, and then it had a downward.
Right.
All because it had the acceleration of gravity acting downward on it. What about the horizontal component? It stayed the same. So I can immediately find the horizontal component when it came off the bat because it's going to be the same as it was at the end. The vertical one is different, but what did I tell you about speed? It only depends on the elevation.
Yeah.
And so I can take the vertical component and take the vertical component's magnitude here, and I can immediately calculate what the vertical component would be at the elevation of the bat. And then once I have those two, how do I find the speed when I have the two components?
Could you explain that again with different words?
Appreciate it, yeah.
Well, I will do this calculation so you can see it right now. But I told you that the speed in the vertical direction only depends on the elevation. If you're in free fall. If you're not in free fall.
Oh, yeah, okay.
And so that means we can just use the equation. V final squared will be initial squared plus 2 times the acceleration times change in elevation.
So is it like the vertical never changes because there's no acceleration in the vertical direction?
Horizontal.
Yeah, I'm sorry.
Yes, the horizontal will never change because there's no acceleration in that direction.
Wait, the horizontal never changes because there's no acceleration in that direction?
If there's no acceleration in the horizontal direction, it's all vertical.
But AX is 0.
Right. That means no acceleration. No acceleration means A equals 0.
Right, I get
Okay.
it. Okay, never mind.
Never mind.
Okay, so having thought through how we're going to do it, now we just have to do the work. So we have for the x direction, Vx final equals, I better draw that vector. It has a magnitude of 32.25 in my case. And it has an angle. Which angle is it?
The extra cool fun one.
The what?
The extra cool fun one that we're going to find.
Extra cool fun one. Okay. It was the angle from horizontal, right? Because it said it was 27 degrees below horizontal. So that would have been from horizontal, you see my stripe there, down. In the triangle I've drawn, where would that same angle appear? Okay, I heard inside and outside, and I'm not sure what those mean, so I'm just going to draw it the right place. From the horizontal, right, that's the same as, that's what the words give you. So there's my angle theta, which is what, 27 degrees. So now I need to break this into components. Well, I have my x and y directions here. And so where is the x component in this triangle?
Cosine.
Well, no, where? Just a question. There's three sides to the triangle.
Oh, it's
The one on the top right, bottom, or left? Bottom, okay. So that's the Vx, and then going with what David said, is that the opposite, adjacent, or hypotenuse? That's the adjacent side. It's adjacent because it's part of what makes the angle and not the hypotenuse. Remember, for a right triangle, which is the only kind of triangle that has a hypotenuse, the hypotenuse is the longest side, also known as the side opposite the right angle. So I have, and once again, going with what David said, cosine theta is equal to adjacent, which is Vx, over hypotenuse, which is my 32.25 meters per second. And so Vx, and I should have put Vx final, even though Vx is constant, is 32.25 meters per second times cosine of 27 degrees. I'm not going to worry about calculating that because everyone has different numbers anyhow. So there I have my final speed in the x direction, which is also my initial speed in the x direction. Now, for the sake of this problem, actually, you need to have v final and theta, because you're going to have your answer in terms of the equation. Everyone will have the same answer in terms of the equation. Okay, what about my vy final? Which side of the triangle is vy final? Okay, so we're left with the left side or the top right? Left side, right. And so this is vy final. Vy final is equal to v final times sine theta. Why did I jump immediately to times sine theta? Yeah, I've done this way too many times and I forgot. Sine theta is opposite over hypotenuse. So sine theta is going to be vy final over the hypotenuse, v final. And then since sine theta is opposite over hypotenuse, opposite is equal to hypotenuse times sine theta. So there's my finals in the components. Which one of these was changing? Question we've answered many times. Y. And so now I want to relate the initial and the final y's. So vy final squared equals vy initial squared plus 2ay y final minus y initial. I'm looking for this here. The equation works for x or for y.
You switch that around with the whatever it's called.
Well, I just rearranged. I subtracted 2ay. And now I just square root everything, right? And we need to put things in terms of the variable names they gave us. Right, so I put v final here. Is that what they called it? Yes, they did. And they called it theta final, so I should have put a final on my theta there. So vy final was v final squared sine squared theta final. That's, I squared both of the items. Ay is minus g. So minus a minus g is plus. Is everybody cool with that? So I don't want people to come back. Actually, I'm going to write it out still. Okay, I changed colors too soon. Minus 2 minus g. And then y final minus y initial is h. That's the symbol they gave us, going with what David wanted to use all along. And so there's an equation. Now notice it has a plus and a minus. Well, we know the vy initial was up, the vy final was actually down. I didn't put a minus sign here because I was just looking at the magnitudes. But if you look at the direction, if you start here, that's in the minus y direction. with the plus x direction. So here's my Vy initial, and now my final step. How do I combine these to find the initial speed? It does say the initial speed, right? Or does, oh no, the first one is just in the x direction. Oh, we found that long ago, right? Just in the x direction was this. Yes, that was final, but the acceleration in the x direction was 0, which means that the x component was staying at the same speed all throughout. And then the next one was the ball's initial vertical, which is what we just found here. And notice I have y subscript 0. They have, or I have v sub y0. They have v sub 0y. That's a personal preference issue. Basically, names are always personal preference issue. So we've now found B's answer. Now for part C, we need to find the magnitude of the velocity. So how do we find the magnitude based on A and B? Yeah, we use the Pythagorean theorem. We have two components, one horizontal, one vertical. Horizontal squared plus vertical squared is equal to the final squared. So I have V initial is equal to the square root of Vx initial squared plus Vy initial squared. And you just plug in those two that we found. And then the final question is, find the angle theta. Well, I'm going to draw here. We have the initial we have those values known. I want to find, seriously, give me a different color. This angle, how do I find that angle from those two values? I have the opposite side and the adjacent side. What trig function relates those? Tangent. And because I want the angle, then I use what Sarah's been trying to tell me, inverse tangent. Or and there I put tangent to the minus. When I try to write it different ways, so you remember that it's written different ways all the time and you have to be flexible. All right, so actually we did do all the entire thing because never were there numbers actually put into the problem. Oh, wait. The rest of them don't say in terms of the variables. So the rest of them you do put the numbers in. I did everything in variables. So it turns out the method or the actual math work was not very hard. It was the ideas of which equations I have to put together and why. That's where the hard work is. That's where the physics is. I shouldn't say it that way because it makes it sound like physics is hard. But physics is fun. It does have its challenging aspects. I'm not going to deny. But I love physics. No. No. But you have to apply yourself. That's not something I did regularly.
You gotta admit that to a class. Look at how you're honest.
Okay. True unrelated story. I came to German class one day and I talked to my classmates. Hey, what are we doing in class today? What are we covering? They look at me like I'm an idiot. The test? And I was like, the test over what? That's the kind of student I was. Yeah, I got better. Okay, so this is actually the same slides from last class period because we didn't get to the forces part last class period. So today we're going to do the forces part. So just zooming forward to the, whoops, one too far, the forces part. Sir Isaac Newton is always the person we turn to when we talk about forces. Sir Isaac Newton wrote his masterpiece, Philosophiae Naturalis Principia Mathematica, something like that. It's usually just called Principia Mathematica. In 1687, I have never read it because, well, I'm still not that great a student. I don't read things. But I've been told that it's virtually impossible to understand this book. That it's not written in a very clear manner. But he lays out all of these important things he discovered. And I have to talk about how he discovered it because, well, A, it makes me feel good about, me and my brother and whatnot. Isaac Newton, and as we'll learn later, Albert Einstein, they were not your best students. Isaac Newton, from what I've read, when he was in grade school, he'd come to class and he would make his little inventions to impress the ladies. And he wouldn't do what the teacher told him to do because teacher bored you, right? I mean, you can all relate to that. Absolutely. I'm experiencing this right now. And so after he finished the compulsory education, which was like through 6th grade, they said, well, he's going to have to get a job because he's not cut out for school. And so somebody found him a job working as a shepherd. As he worked as a shepherd, what do you suppose he did? He didn't watch apples. He made little inventions to later show the girls and impress them and stuff, And so as the sheep wandered away, he was an abject failure at being a shepherd. And so people said, okay, this guy is clearly brilliant, right? Brilliance was not his problem. It was doing what the teachers wanted him to do that was his problem. And so he was able to obtain sponsorship to go to college. And in college, he continued to be Isaac Newton until his last year of college, when he came to the sudden and harsh realization, if I don't get my act together and do what the man wants me to do, I'm going to have to find a job again. And that was not good. And so his last year, he buckled down, and he got hired as a house scientist for one of the professors, which essentially is the same as being a lab assistant. Or back then, that's roughly the same as being a graduate student. And so then he was working at the college, which was great except for one thing. Those pesky students. He gets to do physics, but then the students come and ask him questions, and he has to go away from his physics to help the students. Now, I love helping students. I don't want you to get the wrong impression here. When you come to my office for help, it is the highlight of my day. So then the greatest thing that ever happened to Isaac Newton occurred. The Black Plague. People were dying. And of course, it's a communicable disease. They didn't understand how it was communicable, but they didn't want all of their youngest and brightest minds to all die together. And so they canceled school for something like 18 months. And so then Isaac Newton gets to do whatever he wants. Now I'd be at my sister's house, now I'd be at my house in Colorado, but my sister's house in Huntington Beach is still pretty sweet place. But Isaac, he went to his grandma's house. And why his grandma? Because his dad died when he was a child or an infant. His mother remarried when he was like 2, and his mother's husband said, hey, that's not my kid. I'm not raising him. And so he was raised by his grandmother. So he went to his grandmother's house and did nothing but physics. Imagine the joy in his life. And so during that time, he came up with the 3 laws of motion that we're going to introduce today. Also his law of universal gravitation. But he realized that there was no math in existence that would allow him to solve these stinking problems. So he invented calculus so he could solve these problems. How old was he? I think he was like 27 or something. All great scientists are under 30. There has been some shift in the last 20 years or so, but essentially all great discoveries occur before 30. We become too indoctrinated and set, and this is the way things work.
We got 10 more years.
Yeah, do it now. That's right.
Maybe most people stop dying as young.
Yeah, we stopped dying as young, but like Albert Einstein. Albert Einstein felt like a failure because after his great breakthroughs in 1905 and the further refinement that finished around 1918, he didn't have any more breakthroughs. And he felt like he was just a flop. which is crazy because, of course, the guy was incredibly influential to our lives. So, obviously, Isaac Newton, very important to physics. You know what he did in his spare time besides physics? What?
Calculus.
Calculus. Math. That would just be included in his physics.
Wooing women of wonderful inventions.
I don't know about his love life as an adult, but he wrote a lot about theology. That was his other passion. He also became a politician for a short time, and he's on record as speaking once. And that one time, everybody's like, ooh, the great man's going to say something. And he said, it's getting a bit drafty in here. Can we close the window? He was a great politician. Anyway, we call our unit of force a Newton based on Sir Isaac Newton. And I think you can now see he really was important. So a force. There were great discussions in the Peruse all about forces. A force is anything that pushes or pulls. That's not a naive notion that has to be refined. That is what a force is. And as the textbook says, this is a good starting point. Somebody says, does that mean that we're going to have to, redefine it later? No. It was saying it's a good starting point, and then they pointed out that if you push or pull, there's a direction to it. I can't push on you and not have a direction to that push. And so force is fundamentally a vector. It has a direction. So it has a magnitude and a direction. It's a vector. Oksana.
Instead of saying or, like is it or pull?
Yes.
Wouldn't it be like a logical operator and?
No.
Well,
Because let's say I push on Andy. I'm not pulling on her. I'm only pushing.
But for Newton's third law of motion, it's for every
Action
reaction.
is equal to reaction.
And I push before.
But those are different forces, and they're actually either both pulling or both pushing. But
Isn't that like if you push me in pushing me and my arm is also pushing you? So there's
that's Newton's third law, yeah.
okay.
And that's what it's not like shouldn't be.
Well, because and would imply doing both at the same time. So anything that pushes or pulls. So one of the forces that we're really comfortable with is weight. The weight is the force that gravity is pulling on me with right now. What direction is gravity pulling me? Down. So my weight is downward. And my weight, what are the units of weight? That's mass. Okay, Russell says stone. Sure. Sure, you can count my weight in stones. We're not going to contemplate how many stones it is.
What type of stone?
Newtons. My stone's 20 pounds.
It's like a British.
It's like 14 to 13.
I thought it was 20. Okay, well, who cares? We don't use stones in America, but they do in England still. They'll say somebody's this many stones. So stones are a unit of force, a unit of weight. Newtons are the ones we're going to use, the unit of weight. And we'll get to I've got an equation here, so I'll work out the units for it right now. And pounds are a unit of weight. So here we have an equation. Now, our textbook uses W for weight. I always use an F if it's a force. My symbols for force will always start with an F. And so I put F sub G to mean the force of gravity for weight. So when I write things, I will write things like, whoops, forgot to turn on the pen. So I will write right now. I swear I put it on pen, not on laser pointer. Pen. Yeah, see, it was writing. I put F sub G equals instead of W. What are the units of mass? Okay, it's actually kilograms. Pounds are force. Grams are a unit of mass. If you use the CGS system, they use centimeters, grams, and seconds. But we use the MKS, meters, kilograms, and seconds. So it's not like you're wrong, but it's not the standard MKS. So we have kilograms, and then G is the acceleration of gravity. What are the units for acceleration?
So meters per second squared.
Meters per second squared. So the unit of force is a kilogram times a meter per second squared. And that's a bunch of words to say. And so we just shorten it and say that's equal to a Newton. We use a capital N for the symbol Newton. If you write out the word Newton like he has a weight of 7.5 newtons, which would be a real dumb small weight. It would be more like 750 newtons. You would write the N with the Newton with the lowercase n to distinguish it from Sir Isaac Newton with a capital N. So that's just some naming conventions. I am not going to test you on how you write out the word Newton, but you'd better use a capital N for newtons because that is a definition for it. Now, somebody said, why isn't this a simple fundamental standard like a kilogram is? Well, I say a kilogram is like a kilogram has been for 3 months now or whatever.
America.
Huh?
America. No, we changed things for pounds.
Oh, no. No, the up until it was somewhere around May, the definition of kilogram was there is a block in France. That's the definition of kilogram, which is pretty hard to define. But they've redefined the kilogram so now it can be reproduced anywhere around the world. So it now has a very solid reproducible value. The meter has a solid reproducible value. The second has solid reproducible value. And so this is based on fundamental things. So there is a very specific value for the Newton. It's not something that's kind of fuzzy. Okay, so the weight gravity on the right-hand side is a common force that's based on the fundamental force of gravity. There are only 4 fundamental forces. Gravity is one we react or interact with all the time. Do you have a question, Andy?
No.
Okay. So gravity is one of the 4 fundamental forces. Anybody know the other fundamental forces?
Almost like nuclear.
Electromagnetic, what did you say?
Strongly nuclear.
Strong and weak nuclear. Okay, so those are the 4 fundamental forces. These here are listed in the generally accepted strengths. The weakest of them is gravity, then the weak nuclear, then the electromagnetic, then the strong nuclear. It depends on how far away your objects are, which one is actually going to be the strongest and weakest. But gravity is considered the weakest, even though if you study astronomy, gravity is the one that wins. Gravity always wins, even though it's the weakest one. The reason is gravity is long-range. Gravity and electromagnetic are long-range. Those are the only 2 we're going to talk about until the very end of second semester because they're long-range forces. The strong and weak nuclear forces are very short-range. What's the difference in gravity and electromagnetic force? As we'll learn, they're almost exactly the same equation. But the difference is the charge for electric force comes in 2 poles. We call it a dipole. You have positive charge and negative charge. And so you can have an attractive or repulsive force. And if you have a whole bunch of charge, on average, you have 0. Gravitational charge, which we call mass, is unipolar. It only comes in one type, positive. And so if you have a big object, it just has more gravitational charge and thus a stronger force that it produces. So that's why gravity ends up winning in astronomy every time, because you have big massive objects. This force just gets bigger and bigger and bigger. This one here is staying close to 0. Okay, so those are the fundamental forces, but they're not the common forces. Now we talk about force of gravity as a common force, but what are the other common forces? Normal force. Normal here does not mean standard, ordinary, everyday. I didn't hear what you said there.
Orthogonal.
That is what it means. Normal is a 3-dimensional equivalent to perpendicular. Orthogonal is a multi-dimensional equivalent. So orthogonal, you could have 7 different directions, and orthogonal is the word you use there. So normal is the 3-dimensional equivalent to perpendicular. So normal forces are forces that are acting normal to a surface. Well, I still really haven't defined that, have I? I just said it's a word kind of like perpendicular. So the normal direction to a surface is the direction coming out of the surface. So the floor is horizontal, the direction coming out of the floor is vertical. So vertical is normal to the floor. So the normal force, yeah, go out there and use my saber. I don't know the difference in a peg or a saber. But. So if I stand here, let's talk about the force you already knew. What force was acting on me? Gravity. Pointing what direction? Down. I'm not going through the floor because there is a normal force that's coming directly up out of the floor. And so that's a very common force. It's important to remember the direction of the normal force is which direction?
The opposite. Perpendicular.
Coming out of the surface, normal to the surface, hence the term normal. So if I push on the wall, what direction is the normal force from the wall on my fist? Pushing that direction, horizontally. Because we get so, just like I was talking about using cosine and sine to break vectors into components, we get so used to our normal force being vertical that we forget that normal doesn't mean vertical. And so we'll have a slope like this. What direction is normal to my meter stick? This way. And people will put the normal like this because that's what it would have been if it was horizontal. Okay, Randy, you had a question.
I forgot. I was like, say it.
Sorry, I kept rolling until I got to the end of my thought. Andy.
Wait, okay, so that makes sense to me, but how does that relate to orthogonal and disorthogonal?
Orthogonal means mutually perpendicular. So if you have 3 dimensions, which is what we have for spatial, you can use your hand and this is orthogonal to this is orthogonal to this is orthogonal to this. So we say they're mutually orthogonal. Right? I could have said this is perpendicular to this because perpendicular is a 2-dimensional word. But to encompass all 3, we use orthogonal. And if you have, like, let's say we're dealing with 7 additional spatial dimensions, because if you are doing string theory, I believe that's what they say, is you have 7 additional spatial dimensions. Well, how do you find, perpendicular to 10 directions? Well, you use the word orthogonal, but they're all mutually orthogonal.
I don't really understand that, but I will.
None of us do. Russell.
What are the other dimensions supposed to be doing?
No idea. No idea. Okay, so that's the normal force. Then we have tension. Tension is a force that's distributed through some kind of flexible thing, like a string or a chain or something. A what? A sinew. Sure, that works too. So a tension force is a force distributed through something like a string, and whenever it touches something, it applies a force in the direction the string is leaving. So here, the string is leaving my left hand in the vertical direction going up, so the force of tension is pulling my fingers up. At the top, it's leaving going down, so it's pulling my fingers down. And I could do something like here, put out your finger. Do something like this, and it's leaving her finger in 2 different directions, right? So it's pulling down and pulling up and to the right. So that's how tension works. It's distributing a force. In our idealized world, our strings will have no mass, and they won't stretch. That's what we call an ideal string. Doesn't stretch and doesn't have mass. In that case, the tension and of course no friction, because come on. In that case, the tension in the string will be uniform everywhere, and it makes life easy, which is why we make those rules. Yes?
A couple of days ago on Kurzweil, there was some questions about sag.
Mm-hmm.
Can you answer why something doesn't go back to its original position after the object of mass has been removed?
It's what we call permanent deformation or plastic deformation. If you have something that was like this and you permanently stretch it, it's not going to come back to being flat again. If you didn't permanently stretch it, it would come back to being flat. So it's permanently deformed. Huh?
Will it ever go back to its original?
It's going to depend on the material. Some materials may very, very slowly return. Some may be permanently deformed. If I take this and I pull it hard enough, it'll be permanently stretched. It won't come back to this, but if I just pull a little and let go, it comes back. And so it's elastic deformation here as it comes back. If I pull it permanently deformed, then it's plastic and it won't come back. And that's basically what you're dealing with there. Okay, continuing on, going past tension and additional forces, we have a spring force, which is why I have this out here. This is an example of a spring. A spring can be stretched. If you stretch it, it will pull back. We call it a restoring force because it's going to try to pull back to its equilibrium configuration. Equilibrium means equal forces. The Libra's force. If I compress it, it has a restoring force to try to push it back again. The magnitude of that force depends on how much I deform it from its equilibrium, how much I stretch it or compress it. And it's restoring, so it's always trying to get it back. There are people talking about like spring constants and stuff like that. The spring constant depends on what you made the material out of and how it's designed. So different springs, each one will have its own spring constant that depends on it. And I'll show you some pictures of springs coming up. But that's another item that we're going to use that has forces. Friction force. Friction force is really vital. Like we drive cars, we walk. If I want to walk, I mean, you can say, oh, well, lift your foot and move it forward, and of course you fall forward. If you try to do that on wet ice, you fall down. Why?
No friction.
No friction. Friction is the thing that's pushing you forward. Friction is also the thing that makes it so when you put this foot down, it doesn't just keep sliding forward. If it wasn't for friction, we would just be doing the splits every time we tried to walk. And in your car, if you put your car on that wet ice and you try to go, what happens? You just spin.
I got all-wheel drive.
What was that?
I got all-wheel drive in snow. And Audi.
So friction is the thing that makes your car go. It's the thing that allows you to walk. It's very important. We sometimes say, friction, it causes us so much problems, but it causes us also to be able to do fundamental things. So friction is a force that acts between two surfaces to keep them from sliding against each other. We call it static friction if they're not sliding, or to oppose their sliding if they are sliding. We call it then kinetic friction if they're sliding. Maybe.
With friction still, you know how we ignore air resistance all the time? Is that still friction in a way? Because we're pushing against.
We will be, because friction is very important, we generally won't be ruling out friction, but we'll say a frictionless surface a lot. So when we say frictionless surface, then we're saying, hey, magic, no friction. And other cases, we'll just say the coefficient of friction is this, and you'll calculate it. So friction comes into two types, static and kinetic. The static actually is always greater than or equal to the kinetic friction. That is, if you have two surfaces that aren't sliding, it's always greater than or equal to the frictional force you have if they were sliding. That's part of the reason your car has anti-lock brakes. The anti-lock brakes will take it up to its highest static friction. As soon as it starts to slide, it'll release and then start braking again. And so you don't have sliding surfaces, you actually have a higher average frictional force, which means you can slow better. And also you can steer, which is a great advantage. Whereas if you're skidding, you have no more steering. Okay, another force, air resistance. Air resistance, when I was a kid, we'd be driving from Monterey Bay Academy to Santa Cruz. I'd be sitting there with my hand out the window going, phew, playing with the wind. That's air resistance. We all feel it, we know it exists. For almost all of our problems, unless you're specifically told to include it, we will assume no air resistance. If things are going really slow, the air resistance is minimal. And so that's reasonable. If they're going fast, well, I mean, just this fast, I can feel it, right? Then it's no longer completely ignorable. Finally, buoyant lift fluid pressure. I just combined these all together. They're different ones. But we will talk about fluids near the end of this semester. We'll learn about some forces, buoyancy, the thing that helps us to float, lift, the name for the force that makes an airplane fly or that makes a sailboat sail, and fluid pressure, force per unit area. It's a slightly different thing. Yeah.
What about thrust? The book mentioned something about thrust.
Okay, thrust. Thrust is actually taking Newton's second law in the calculus form, and it's how we calculate the force that's being produced by a propellant that's having its momentum changed.
What about lift?
That was on the list.
Lift is,
Lift is the result of Bernoulli's principle having different pressures on top and bottom. Okay, Newton's three laws. I'm going to have to stop with Newton's three laws. So at the end, my review, which should be starting right now, would be we learned about forces, we learned about Newton's three laws. So Newton's three laws. Newton's first law is called the law of inertia. If you were to go back to the time of Aristotle, Aristotelian thought said, if I take this tape and I slide it along here, it stopped. That was clear and obvious. Why did it stop? Well, it must be that stopped is its natural state. And so things go to their natural state. If I apply a violence to this, like pushing it, that made it unnatural, but then it returned to its natural state. That was Aristotelian thought. And it came to Galileo, who said, I don't think so. I think that there had to be a force, something that pushes or pulls, that made it stop. And if there was no force, it would have just kept going at constant velocity forever. Constant velocity means the same direction and the same speed. And so Galileo was the person who came up with this concept of inertia, that an object will stay in constant motion unless an object acts on it. And so that's Newton's first law of motion. It takes a force to make something's motion change. The second one includes the first one. The second law, if you know the second law, you automatically know the first one. Because the second law is saying, well, how is an object then going to respond to a force? And so the second law says, if I put a net force on an object, so here's my object. If I put a net force on it, net force means I add up all of the forces acting on it, then it's going to accelerate with its acceleration equal to the net force I applied. Remember, force is a vector, so it's going to have direction with it, divided by the mass of the object. So if I have two objects of differing mass, and I put the same force on them, Newton's second law says the more massive one will have a smaller acceleration. Which is like saying if I have somebody that's, well, I got a golf ball in my hand. Let's say I have a golf club. I've got the golf ball on a tee and I've got a bowling ball on a tee. And I take a mighty whack at this golf ball. What's it going to do? What's the golf ball going to do? It's going to go flying off. Because that force applied to this little mass made it accelerate quite a bit. And if I do the same thing to the bowling ball, what's going to happen? Yeah, my club's going to break. Because the bowling ball had a much bigger mass. Inertia is a measurement of mass. Inertia is how much it's resisting a change in motion. Mass is that measurement. Because it had a much bigger mass, it resisted the change in motion much more. And actually the force got bigger on the club because of that and broke my club. The last one there, Newton's third law. For every action, there's an equal and opposite reaction. In that statement, action means force. So for every force, there's an equal and opposite reaction is returning force. So once again, coming up to Andy. If I put a force on Andy, according to that law, Andy is putting a force on me that's equal in magnitude but opposite in direction. So I was pushing on her, she was pushing on me with equal forces. Now there was a lot of discussion about this. This is an easy one for students to get confused about. If I have a VW bug run into a Peterbilt truck, which one is going to sustain more damage?
The beetle.
The bug, yeah. The Beetle is going to be damaged much more than the truck. Which one has more force acting on it? Neither. They have the same. Newton's third law says it's the same. People get really confused. They're like, that bug is destroyed. The Peterbilt doesn't even have a dent. The difference is the ultimate strength. The Peterbilt is made out of much stronger material, and it also has more mass, so it's not going to be affected very much. It's not going to slow down nearly as much as the bug does if you have a head-on collision. and it's not going to crumple like the bug will. And so it's the ultimate strength, how strong it is, that deals with the damage done. But it's going to be the same force either way. So to end, if I was really angry with David, and we're like holding each other's arms so we can't punch each other, and I'm like, I'm going to headbutt him, and I go, whammo with my head into his. Who has more force acting on their head? It's the same.
No one wins with a headbutt.
Why would I do this then?
Your head might be harder than his.
My head might be harder than his.
My head is wasteful to impact, where his isn't.
Okay, there are some reasons that you might do this. You are braced for impact. That means your head's not going to go whoink as much as his, which means you're going to cause less bruising in the brain. You're still going to cause bruising in the brain, just not as much. Also, I could be smart and I could choose to headbutt him in the nose. If I headbutt him forehead to forehead, we're just having two hard pieces of bone hit each other. That's just going to hurt us both. If I headbutt him in the nose, what's going to happen? His nose is going to crumble. I'm still going to get some gouges in my head, but I'm going to hurt it more.
Okay, so since you're higher up than he is, will the acceleration down from gravity add to the force that you're putting onto him, or will it still be the same?
It would only help me have a higher speed.
But if you're a component of gravity, since you're not actually going down, you're going.
Like,
Sure.
would there still be the same forces though?
It's still going to be equal and opposite forces. So I'm going to hit him harder, which means he's hitting me back harder.
Okay.
Okay, have a happy Sabbath, y'all.
You too.
Thank you.
Move.